Hey everybody, Dr. Bennington here with a short tutorial on metamorphic rock identification. What I'm going to do is walk you through the main types of metamorphic rock, and we'll look at some of the characteristics that help geologists identify particular types of metamorphic rock. So to start with, what is metamorphic rock? Well, metamorphic rock is rock that starts out as some pre-existing type of rock, either sedimentary rock or igneous rock, or some other kind of metamorphic rock, and then the pre-existing rock, which is called the parent rock, is somehow affected by heat and pressure, which changes the characteristics of the rock into a new type of rock, which we call metamorphic rock. Most metamorphic rock is formed when tectonic plates collide and large regions of rock become buried deep beneath mountain ranges in the roots of a mountain range, where the rock is subjected to progressively more and more heat and pressure as it's buried deeper and deeper in the earth. And so metamorphic changes start out being very subtle and over time can become increasingly drastic. Some metamorphic rocks are relatively little changed from their original parent rocks, and other metamorphic rocks have gone through tremendous changes and are basically unrecognizable compared to what they started out as. Like any type of rock, metamorphic rocks are identified on the basis of two main characteristics, their mineral composition and their texture. Mineral composition in metamorphic rock is very similar to mineral composition in igneous rock. The dominant minerals that you find in metamorphic rocks are all silicate minerals. So for example, we have quartz, we have the different types of feldspars, in particular albite and K feldspar are the most common feldspars in metamorphic rocks. Hornblende, an amphibole, is a very common constituent of metamorphic rocks. Mica, both biotite and muscovite, commonly occurs in metamorphic rocks. And then one type of metamorphic rock, marble, is made up of the mineral calcite, the only non-silicate mineral on the page here. Another mineral which commonly shows up in metamorphic rocks is garnet. And the reason you find garnet in metamorphic rocks is garnet tends to form at high temperatures and pressures deep in the earth. Now, as far as metamorphic textures go, basically metamorphic textures develop depending on the kinds of minerals that grow in the rock, but also whether the rock is subjected to mostly heat or to heat and pressure, or lots and lots of pressure. So we can divide metamorphic textures into two main groups, foliated, and foliated refers to some kind of layering in the rock, some non-randomness to the fabric and the mineral grains in the rock. And then we have non-foliated metamorphic rocks. And non-foliated metamorphic rocks are rocks that don't have any obvious layering, don't have any obvious orientation to the mineral grains. Most metamorphic rocks tend to be foliated. There are a couple of types that are non-foliated, as we'll see. So if you start out with a very common type of sedimentary rock, say shale or mudstone, and you bury that rock under a rising mountain range and heat it up and bring it under increasing amounts of pressure, what happens is the clay minerals in the rock begin to reorient themselves. They begin to kind of flatten out in response to the pressure gradient, and they will start to recrystallize into new minerals, into a mineral called chlorite and mica minerals. And as they're recrystallizing, the grains are starting to grow and become a little bit larger. So the clay minerals are very microscopic, and they start to change into new kinds of minerals. They reorient themselves and they begin to grow. And the first stage in metamorphism, starting from say a shale or a mudstone, is a slate. And slates look like shales. They're layered. They're kind of dull looking, but they're a little bit different from shales because they tend to be very well layered. We call that a cleavage. So shales will split into even flat pieces, and we call that facility. But when you create layering because you reorient the mineral grains in the rock, that becomes a rock cleavage. So shale has very good cleavage. It splits into nice even flat pieces, which is why we like to use it for roofing material and for tiles. If you look carefully, there's a slight shine on the surface of shale. The color can be highly variable. Most shales are black or gray, but you can also get green shales and you can get red shales depending on mineral impurities in the shale. So if you pick up a piece of shale and turn it, you see that it tends to split into very flat pieces. And you can look for this very subtle shine, just a hint of a shine on the surface. And just an overall kind of dull appearance. Now, if you take a slate and you bring that rock under increasing amounts of pressure deeper in the earth, the mineral grains in the rock will continue to recrystallize. They'll continue to grow, and you'll get a different kind of rock, which is similar to a slate, called a phyllite. And phyllites have a little bit more of a shine on their cleavage surfaces, right, on the broken surfaces, because the mineral grains are getting larger and they're reflecting light better. Otherwise, phyllites tend to look like slates, except that very often they're kind of irregular and folded, so they're not quite as nice, and the pieces aren't quite as nice and flat as pieces of slate are. Also, because of the growth of a particular type of mineral called chlorite in phyllites, many phyllites are greenish or greenish-gray in color. So if you pick up a piece of phyllite and turn it in the light, you can see that it has a little bit more of a shine to it than a slate does, and it's a little bit more irregular in the way that it breaks. Now, as metamorphism continues, and those mineral grains continue to recrystallize and regrow, eventually they will become large enough to be visible to the naked eye, and that gives you a schist or a mica schist. And mica schists are very easy to recognize. They're very well foliated, which means that they have a very good layering. It's easy to see the layering. And the layering is produced by these large, platy, very glittery-looking crystals of mica, which stack up in flat sheets in the layering of the rock and create what we call a schistosity. And if you take a piece of schist and you turn it in the light, you can see these grains of mica. They look like glitter. So mica schists have a very glittery appearance. Looking edge-on into the layers, you don't see as much glitter, but when you look at the cleavage surfaces of the rock, you see all of the platy mica grains that are all kind of laid out one on top of the other. A lot of schists will exhibit what's called a porphyroblastic texture. Porphyro means different sized, and a blast is a grain. So what that very sort of scary looking word simply means is that within the schist are large grains of some other mineral. And typically that mineral is garnet, although there are other minerals that show up in schist. But very, very often embedded within a mica schist, you will see large crystals, sort of dodecahedral crystals of purplish or reddish garnet. And we call that a porphyroblastic schist. Here's an example. You can see in this specimen, this is a very fine-grained schist. The flakes of mica are very small, but you have these beautiful ruby red crystals of garnet that have grown up within the layers of mica and kind of pushed the layers of mica aside as the garnets have grown to disrupt the nice even layering in the rock. Now, sort of the last stage of metamorphism, starting from a mudstone or a shale, is gneiss. And what happens in a gneiss is because of the tremendous pressure and shearing that the rock experiences deep in the earth, minerals become segregated into distinct bands or layers, and the rock takes on a very well-foliated, well-layered, but distinctly banded or striped appearance. And very often in gneiss you will get alternating layers of lighter colored mineral, quartz, feldspar, and darker colored minerals, say amphiboles or micas, that give the rock kind of a zebra stripe or a tiger stripe appearance. So gneisses are fairly easy to recognize. You look for the stripes or the bands. And you can see the different minerals in this rock. The grayish-looking glassy mineral is quartz. The lighter-colored white mineral is feldspar. And then the darker mineral forming the dark bands is hornblende. A similar kind of rock is an amphibolite, and amphibolites can go by other names. Another name for an amphibolite is an amphibole gneiss, because amphibolites have a similar texture to gneisses. Another name would be a hornblende gneiss, because the main amphibole mineral is hornblende. Amphibolite is kind of the mafic equivalent of a gneiss. It's a gneiss, but a gneiss that's composed primarily of dark minerals, usually hornblende and biotite mica. So here's an example of an amphibolite, and you can see that the rock is mostly made up of dark mineral with a few layers of lighter colored mineral in between. And on the cleavage surface, you see these beautiful needle-like crystals, very elongated, thin crystals of hornblende. Right? So amphiboles very often form these needle-like crystals. You might also notice there are some red blobs within this piece of amphibolite. Those are garnets. So this particular specimen of amphibolite has some porphyroblasts. It has some small garnets that have grown up within the body of the rock. Now, the last two examples of metamorphic rock are non-foliated metamorphic rocks. So if you start out with a limestone, which is a sedimentary rock made out of calcium carbonate, when that rock becomes metamorphosed, the calcium carbonate doesn't change into a different mineral. What happens is the tiny grains of calcium carbonate combine and regrow into very large grains of calcium carbonate, otherwise known as calcite mineral. And so marbles tend to have a very flashy, kind of cleavagey, blocky appearance because you have these nicely formed crystals of calcite that have very good cleavage surfaces. One way that you can recognize a marble is just like a limestone. If you put a drop of dilute hydrochloric acid on the rock, the acid will fizz or effervesce because the hydrochloric acid reacts with the calcium carbonate mineral. So here's a specimen, and we pick it up and turn it in the light. You can see very flashy cleavage surfaces, which are the calcium or the calcite crystals. And if we apply a drop of acid and zoom in, you can see the acid is bubbling away as it reacts with the calcium carbonate mineral. There's another non-foliated or non-layered metamorphic rock, which is called quartzite. And quartzite is similar to marble in that it's non-foliated, so it doesn't have much of a layering to it. And it's made up of a mineral that forms kind of blocky crystals instead of flat or elongated crystals, but in this case the mineral is quartz. So quartzites look a little bit like marble, but they're not very flashy and cleavagey like marble is. Instead, they have kind of a sort of a granular sugar sort of appearance. We call it a sugary texture, and that's produced by kind of large grains of quartz that have grown and interlocked together. And quartzites tend to be very hard because quartz is a very hard mineral, and they will not react with acid. So if you pick up a specimen of quartzite, it looks a little bit shiny because of the quartz, but you don't see flashy cleavage crystals or cleavage planes, and it will not react with acid. So it has that sort of sugary texture, but no reaction with the acid. All right, so those are the basics of metamorphic rocks. I hope you found this enlightening, and I invite you to review the other presentations on igneous and sedimentary rocks as well. Thank you.